The New Quantum Era,
a podcast
by Sebastian Hassinger
and Kevin Roney.
Welcome back to our podcast. We're very excited by our guest today. We think you'll enjoy this episode. We're joined by Dr. John Preskill today. He's a professor of physics at the California Institute of Technology and quite famous in the quantum computing field for having coined the term NISQ, Noisy Intermediate Scale Quantum Computers. He wrote a paper in 2018 that really characterized the types of devices, the more sophisticated devices that were being produced, but also called out a lot of the challenges that those technologies are still trying to overcome. And his work has continued to be really at that intersection of what the art of the possible is from both a technology and a scientific perspective with the devices that are made and are made available today.
Should be a fun ride because he's also one of the ringleaders of the so-called, it from qubit intellectual movement. I guess studying the intersection of quantum gravity theory and quantum information sciences. So it's going to be a good time.
Yeah, what I find really interesting about John is that in a way, his interest in quantum computing is motivated by the ways in which it can help progress our understanding of quantum mechanics, specifically quantum gravity, quantum matter, and as you said, sort of that broader set of topics that are known as it from qubit. We'll dig into the information paradox in black holes, for example, and what error correction might be able to tell us about that phenomenon. So it'll be great. So let's jump in.
Here we go.
Hello, and thanks for joining us again. We've got a really special guest with us today. We're extremely excited to be speaking with John Preskill. He's the Richard P. Feynman Professor of Theoretical Physics at the California Institute of Technology, or Caltech, where he's also the director of and I think founder of the Institute of Quantum Information and Matter. He's played an instrumental role in the foundation of the field, the development of quantum information science, famously coining the term NISQ, or Noisy Intermediate Scale Quantum Computers, to describe the devices that we're building today in a paper that was published in 2018 that's still, I think, critical reading for understanding the field as it is today. So we're very excited to have with us John Preskill. Welcome, John.
Oh, I'm excited to be here with you guys.
Welcome, John.
Thank you. And we always like to start off, John, just by giving our guests a chance to sort of tell their story a little bit, because the path to quantum information science is so varied. You, I think, began as a particle physicist. So how did you sort of make your way into this interest in quantum information?
Well, actually, like a lot of kids of my generation, I got excited about science because of the space program. I remember the day that Yuri Gagarin orbited the Earth. It was an electrifying moment, and then followed very avidly all the missions of Mercury and Gemini and Apollo and so on. And, so then I wanted to learn about rockets and things like that. But
amazing days, yeah.
Yeah. I got interested in math, and, in high school, I decided the greatest achievement of the human intellect was Gödel's theorem. The idea that that there are things that are true, but which we can never prove, I thought was fascinating. So I thought, okay, I should be a mathematician and do set theory and logic. And that's what I had in mind when I went to college. After a year at Princeton, which I'd gone to because somehow I thought that was the right place to do math, I think I wised
up. There are worse places.
I kind of wised up that maybe I wasn't going to I wasn't cut out to be a mathematician. But meanwhile, physics is even better, right? We can use math, and we can understand nature uh, by using mathematical ideas and methods. Now, this was a time when particle physics was really taking off. I was an undergrad in the early 70s, and so the Standard Model was being established, and quantum chromodynamics was discovered, and charm was discovered. And there was something very deeply appealing about studying nature at the most fundamental level. And so that's what I wanted to do. I went to Harvard for graduate school. Now, the sad thing is that for my generation, we came along just a little bit too late to take part in discovering the Standard Model and establishing those truths. But it was okay. We were going to do the beyond the Standard Model physics, right? So I got interested in cosmology because we had all these speculations about physics at really short distances that we couldn't explore in accelerators. But maybe by studying the early universe, we could find out about physics at very high energies that we can't directly access on Earth. Um, and that was one thing I was interested in. And the other was, ideas about beyond the Standard Model that we could explore in accelerators. We were going to build the great machine, the superconducting super collider, and they started building it. And of course, this was later in the 1990s. It got canceled. But by that time, I'd started to get interested in quantum information because I was interested in black holes. I had to wait for the SSC to come along. Uh, so, what to do in the meantime? Well, there were very fundamental questions I started to appreciate in the late 80s about black holes and how they process information, which was a fairly old thing by then because Stephen Hawking had pointed this out in the mid 70s, but I really began to appreciate it in the late 80s. So, as I've often done, I taught a course about Hawking radiation and how information gets processed by black holes and stuff like that. And that's when I became aware of quantum information as a field of study, several reasons. Partly because I thought, well, I'm trying to understand a very fundamental question about information processing, so I should know what people know about that. But also, Charlie Bennett came to Caltech in the early 90s on sabbatical for a year. And, he kind of um, made me aware that people were studying this. Like he told me about David Deutsch's paper. Incidentally, Feynman, of course, had been very interested in quantum computing, and we overlapped at Caltech for 4.5 years between when I arrived and when he died. And we used to talk a lot, never about quantum computing, because I didn't think I was interested.
Right.
I had seized that opportunity.
Charlie is kind of the Johnny Appleseed of quantum computing in some ways, isn't he?
Yeah.
You could say that. And another thing that was an influence was Seth Lloyd was at Caltech at the time as a postdoc, and he was interested in quantum computing. So I read Deutsch's paper, like the one from 1985. And now what Deutsch did something really important. He formalized the subject. He defined what a quantum computer is in a way that a computer scientist could understand and potentially leap into answering questions about it. But I was very unimpressed by his paper, I have to confess. I missed the point. I thought that he was just talking in very fancy language about probabilistic computing, that, flipping coins to decide the path of a computation. Of course, quantum physics is good for providing a source of randomness. And I didn't think there was anything more to it than that. It was completely wrong. Um, but meanwhile, I was learning about cool stuff like quantum teleportation, and quantum key distribution. And I realized that the information theorists had figured out interesting things about how much information you can gain if you make a measurement.
Well, and I guess Deutsch also laid out sort of the case for information being a physical process, right? There being a physics of information, or the information is understood through physics.
I think computer scientists, at least many of them, the best ones, had an appreciation about that already, but Deutsch was making a really important point that if we build quantum machines, he was arguing that they might be able to efficiently solve problems that we can't solve with conventional machines. It was a fascinating speculation, which at the time I didn't think was very well backed up by arguments. But of course, what was a pivotal moment was the discovery of Shor's algorithm for me. So uh, Shor's paper as a preprint was first started to be distributed in April 1994, but you had to be in the in crowd to get it. It wasn't on the archive, and it was being sent around by email, and I was not in the in crowd. But Arthur Eckert was, and he happened to visit Caltech around that time to give a talk about quantum key distribution. But I heard from him about Shor's algorithm, and I was able to get the paper from him. And I was immediately fascinated because, and I never knew very much about the theory of computation and computer science, apart from my childhood fascination with Gödel's theorem. And but the idea that you can solve problems efficiently that you'd never be able to solve because it's a quantum world and not a world governed by classical physics, I thought that was one of the coolest ideas I'd ever encountered. So I wanted to learn about that.
In your course notes too, you describe Deutsch's problem or the solution relying on non-locality. I think, right? And was it sort of that the insight that Shor was using that mechanism in his algorithm that sort of made you go back and reassess Deutsch's paper or Deutsch's work?
Well, sure. I mean, after Shor, clearly
Right.
would come.
Cat's out of the bag by then.
Now Shor built on a paper by Dan Simon, which came out, just months earlier, which described a problem of no apparent practical interest, for which you could argue there was an exponential speed up, and that actually was what inspired Peter to come up with his algorithm. Yeah, so I taught that course because that's the best way to learn something, right? I think at the time, which was 1997, there maybe Caltech was the only place in the world where we were offering a 1-year class on quantum information and computation, and that solidified my understanding of the subject. Right away, I got interested in the question of whether you can really build these things. I'm not an engineer, but as a fundamental question, it's pretty fascinating. And there were naysayers, and good physicists like Bill Unruh was one, and Rolf Landauer argued very vigorously that you build these things. They understood decoherence, which I was learning about. So, of course, the key thing about decoherence is there's something different about quantum information than ordinary information. You can't look at it without disturbing it. It's not true of classical bits, and it's true of qubits. And the environment is always looking. And decoherence is a very fast process. That's why, in practice, it's very hard to make a cat which is simultaneously dead and alive, because it immediately interacts with the environment and becomes either completely dead or completely alive. And because decoherence is so fast, both Landauer and Unruh argued, uh, we'd never be able to do a computation of any interest fast enough before decoherence killed it.
I can't remember whose slides it was, but I copied it down because I thought it was so hilarious. It was a Landauer quote it may have been Charlie's slides or might have been yours actually, but the quote is, "This scheme, like all other schemes for quantum computation, relies on speculative technology, does not in its current form take into account all possible sources of noise, unreliable and manufacturing error, and probably will not work." That's Landauer's last word.
Well, I talked to Landauer about it at the time, and he had a very forceful way of expressing himself. And he wasn't just worried about decoherence, to be fair. He was worried about the fact, and others were too, that quantum information forms a continuum. It's not discrete. It's not, definitely on or definitely off. So how are you going to control things well enough so there isn't an accumulation of small errors that rotate quantum states a little bit? Landauer was at least as worried about that he was about decoherence.
So the precision of control rather than just the noise of the inherent system or the isolation of the system.
And that's interesting. It's a fair critique because a lot of people showed concern around at the dawn of the analog computing era. That same critique, right?
Of course, Landauer was very well aware of such discussions of
Of that
analog.
same track record, yes, yeah.
We had learned the lesson that you can't control analog information well enough, so you need to digitize it. And then Landauer used to like to open the door and then slam it shut, to make it clear to whoever was listening that there's a big difference between open and shut.
Right.
Whereas a quantum door, there's not such a
Swings
clean
around, yeah.
separation between when it's shut. And yeah, so I got interested in error correction, about which I knew very little. And well, Peter Shor had this amazing run in the mid '90s. He wrote the paper in '94 describing Shor's algorithm. He described quantum error correcting codes in 1995. Andy Steen also did that independently in late 1995. But then there was still a big challenge, which was how are you going to do quantum error correction when the hardware is imperfect? You can't measure things with perfect accuracy. How are you going to keep the quantum computation on track? There was the question of fault tolerance, where everything's noisy. How can you do a reliable computation? And Shor wrote the first clear paper about how to do that in 1996. So, I think there are few better examples in the history of science of somebody having a streak like that, making such fundamental discoveries in rapid succession.
So profound, and it drew so many people into the field as well. I mean, it was just such an inspiration, right?
Lots of skepticism still in the 1990s about whether this could ever work, and for good reason. Here we are. It's
Still working on it.
we're still struggling, aren't we? Though we certainly feel like we're getting somewhere. So big challenge, but a very fundamental discovery. I mean, this isn't just engineering. Actually, it was interesting. My colleagues who were in high energy physics didn't quite get, at least this is true of most of them, why I would be interested in quantum error correction. Isn't that just like an engineering thing? But no, I think, well, it is that, but it's a very fundamental discovery that we can control quantum systems, very complex, very highly entangled quantum systems, and really get them to do what we want them to do with high accuracy. That's an amazing theoretical discovery.
Absolutely, yeah.
Now we're in the process of turning it into reality with actual hardware.
And just the mere force of that Shor discovery of pushing the church Turing thesis back on its heels, right? I mean, that's profound, right?
Right, because as your remark correctly indicates, the question of whether such machines are really allowed by nature
Yes.
was an open question until we about quantum error correction. So, the idea which Shor seemed to have pointed towards that we can solve problems with quantum machines that we couldn't solve with classical machines efficiently. That wasn't going to work unless we could do error correction. And well, we figured it out. It was great.
Well, we figured out theoretically, error correction and fault tolerance in reality are proving to be elusive.
Progress every year, but
challenges.
still a long way to
Progress
go.
every
Yeah.
year. It's true.
It's a hard problem. Well, I was very interested in the foundational questions in those days, where there were a lot of them to think about. What kind of noise models were encompassed by our ideas about quantum error correction? What arguments can we give that those noise models are physically realistic? How can we exploit the structure of the noise to do a better job with quantum error correction? Those are all questions we were thinking about, 20 years ago, and they become increasingly relevant as the hardware advanced.
And is it fair to assume that whole avenue of interest for you eventually led to the so-called "it from qubit" movement? Is that a fair speculation on my part?
Well, of course, that was involved the work of many people. But as I said, I had gotten interested in quantum information initially in the context of black hole physics, and thought about that a lot in the 1990s. And I recognize, for example, the importance of the no cloning principle in that setting. That if the big question, which I guess we haven't explicitly mentioned, was if information falls into a black hole and then the black hole evaporates completely and disappears, what happens to the information? And Stephen Hawking in those days was arguing it's gone forever, information is destroyed. And that was very upsetting for the culture I came from, the high energy physicists. We thought it was a fundamental principle of quantum physics that although information can get all scrambled up and become exceedingly hard to read, it never really gets completely destroyed. And trying to understand how that works has steered a lot of the thinking about how gravitation and quantum physics fit together since really Hawking, 50 years. In 1974, he discovered Hawking radiation, that black holes evaporate. And I honestly think we're making a lot of progress on those questions, but it's still not completely resolved. So you asked about it from qubit. It from qubit was sort of an update of one of John Wheeler's aphorisms. He said, "It from bit." He actually pretty interesting insight back in 1980s and early 90s. He was saying that progress in fundamental physics is going to hinge on bringing in ideas from information theory. And he tried to capture that by saying it from bit. He was good at aphorisms, made up the name black holes and said
Right.
no hair and things like that. Incidentally, Wheeler was one of my teachers when I was a Princeton undergrad. And so he taught a course that I took when my second year as an undergraduate, which covered all of physics in a year. Very idiosyncratic, but he wanted to give us the whole story, from classical mechanics to quantum physics, statistical physics, thermodynamics, and then throw in things like fluid mechanics. And so after that year, we know everything.
It's quite a breadth.
Walk in the park, really. Yeah.
He was an interesting teacher. You'd always come into class immaculately dressed in a suit and tie, and he was a master of the colored chalk, of the illustration. He could draw in real time. But I'll tell you one story about Wheeler, which kind of gives you an idea of his teaching style and his sort of visionary nature, the kinds of questions he would be attracted to. So one day, this class is pretty far along. We've learned all kinds of stuff. And he comes in and he says, "All right, take out a piece of paper. And now I want you to write down all the equations of physics. Don't leave any of them out, and let me know when you're done." Learned a lot of equations, so you could write down Newton's laws and the Euler-Lagrange equation and Schrodinger's equation and laws of thermodynamics. We very busily and dutifully wrote them all down. And then he collected the papers and he brought them to the front of the room and he put them on a table. And then he stood back, was quiet for a moment, and then he gestured towards the stack of papers and he said, "Fly!" Nothing happens. Fly! Nothing happens.
Oh, God.
Then he looks puzzled, and then he turns toward us and said, "I have it on very good authority that these are all the equations of physics, but they won't fly. But the universe flies. Something must be missing." So exactly,
A dramatic flair. That's impressive. Right. In a suit and a tie, too. That's great.
that was something to ponder. I don't really know exactly what he was getting at, but that was typical of Wheeler. He would try to make you think about things in a non-standard way.
Some fun, colorful personalities, no doubt. Yeah.
So actually, it's pretty cool the way ideas which were being developed without fundamental physics necessarily in mind, like quantum error correction, have turned out to be very relevant in other areas of physics. Not just gravitational physics, but condensed matter too, because different types of quantum error correcting codes we now realize can be thought of as different phases of matter with different entanglement and stuff like that. But the idea that quantum error correction had something to do with quantum gravity, uh, it was first hinted at in 1997. Juan Maldacena made this amazing discovery that, at least in a sort of toy model, quantum gravity on a negatively curved space-time, there is a exact correspondence between quantum gravity in a three-dimensional space and a conventional quantum theory in two dimensions. That somehow that extra dimension is emergent from the physics of this two-dimensional theory. That's a realization of what we call the holographic principle. And that came out of thinking about black holes. It goes back to Einstein and Hawking, who said, hey, the entropy of a black hole goes like the area of its event horizon. And that seemed very puzzling because the amount of information you can stuff into a region of space, it should go like the volume, right? But in fact, if you try to put too much information in, black hole forms. And so there's a limitation on how much information you can record, um, which really goes like the area of the boundary of the region. And so that's true not just to black holes, but more fundamentally. And so Maldacena's model was a very nice, fairly explicit realization of this principle that the world, at least in this model, is a hologram. It's really two-dimensional fundamentally, but it behaves for all practical purposes as though it's three-dimensional. You can live there and experience three dimensions just like we're doing now. And um, so, how are you supposed to think about that? There's some kind of dictionary that relates that three-dimensional space to its two-dimensional hologram. And what we eventually came to realize is that that's a kind of quantum error correcting code. You can take this hologram and you can cut pieces out of it, and remove them. But there's a redundant encoding of the information. So deep inside the three-dimensional space, it's very robust. And it's really a kind of quantum error correcting code. To understand how they work, you need to know something about quantum gravity and also about quantum error correction. There weren't many people who knew both.
Is there any parallel that you can draw between Gottesman, Kitaev, Preskill error codes, or error correcting codes, and the holographic projection of three dimensions that you were just describing?
Well, I don't see a direct parallel, but they're both surprising in a way. And so, look, just to give the background, you're asking about a coding scheme which we suggested over 20 years ago. And I guess at the time to experimentalists seemed kind of futuristic, but is now taken more seriously. People are actually doing it with devices. The idea was, instead of using uh, qubits encoded in a two-level system, well, that's not quite the right way of saying it. You can take advantage of a continuous variable system and store information in it, which is digitized, which is what makes it robust. But then you can take advantage of our ability to manipulate a continuous variable system like a harmonic oscillator. It could be, for example, a microwave resonator in a superconducting circuit, which behaves like such an oscillator. It could be the motional state of an ion in a trap, which is another type of oscillator. And the code that we proposed, I guess it was in 2000, is a way of encoding a qubit, or anyways, some finite dimensional system, which is very robust in that continuous variable system. And, it has some potential advantages because we can make really good cavities, which have very good coherence. And as an approach to error correction, it has advantages and disadvantages compared to others. So the thing that's surprising, or one thing that's surprising, is everybody knows about the uncertainty principle. You can't know with precision both the position and the momentum of a particle, and not with arbitrarily good precision. But what this code takes advantage of is that if you consider some quantum state of an oscillator, and then you move it a little bit, you can move it by either increasing its momentum or increasing its position. And you can simultaneously measure both the shift in position and the shift in momentum with arbitrary precision, as long as you promised that those shifts are small. What determines small? Well, it's Planck's constant. What else? That's where quantum physics comes into the uncertainty principle. And this is really how the robustness of the code works, because you can prepare one of these states, which kind of looks like a comb, a grid, where it's a superposition of different possible positions, say, of a particle. And then if that gets shifted a little bit, you can make a measurement of how much it was shifted. And that's true when you shift it in position or when you shift it in momentum. So you can make a measurement that diagnoses that error. As long as the shift is small enough, you can unambiguously correct it.
Without collapsing the state.
Yeah, that's right. And so it's protected. It's protected in particular against the form of error that is our biggest enemy in, say, a microwave resonator, uh, which is the loss of a photon. Okay, so that loss of a photon you can think of as kind of being a little shift in space, and it's something that these codes can correct. And that's one of the reasons that they're advantageous in that setting. They seem to be very well suited for dealing with the type of error which is the most common in that type of hardware.
It's such a cool algorithm. I'd love to hear a little bit more about the background of the thinking and the intellectual history of that time, because I mean, I think for our audience, they're kind of like really vibing a lot on the idea that quantum information science somehow informs the way the surface of a black hole processes information. That's just so fascinating. But is it? I mean, are we correct in speculating that some of that research then came back the other way and informed the thinking around quantum error correction, and there's almost a two-way flow of influence on those two very interesting abstract ideas?
It's a good question, and in principle, it could have happened. I will say this, that thinking about quantum error correction in the context of gravitation led us to construct new types of codes which weren't previously known. Now, whether those codes are actually useful for other purposes, like in quantum computing, that hasn't really been established. But I think having new ideas for how to protect quantum information is something that we'd like to have more of, where eventually we may find applications. As far as quantum error correction, and in particular, this idea of encoding the information in an ordinary harmonic oscillator, we might not have proposed that if not for interactions with experimentalists at the time. In particular, when I found out about Shor's algorithm, there was somebody else at Caltech who was very interested in quantum information in the mid '90s. That was Jeff Kimball, who's an experimentalist, and he's the master of trapping atoms in optical cavities, and had shown that you can entangle atoms by manipulating the electromagnetic field in the cavity, and you can entangle an atom with a photon in the cavity, and things like that. And so in the mid '90s, Jeff was saying, I should be able, up to some cutoff, some limitation, be able to make any quantum state of the electromagnetic field that you want. So what do you want me to make? And so that provided some of the inspiration for thinking about, is there a promising way of encoding information in the electromagnetic field in a cavity? Jeff was considering optical light in a cavity. So what happened later on was Rob Shelkoff in particular and his group proposed the idea they called circuit quantum electrodynamics, where the cavity was a microwave resonator. So there they were manipulating the quantum state of microwave light So I can remember about 20 years ago hearing Rob talk about this idea of circuit QED. It was at a Gordon conference where he still hadn't published on this idea. And Jeff and I were both in the audience, and we talked afterward because we were very impressed by what Rob was proposing. And Jeff said to me, if I were a graduate student now, I'd work for Rob Shelkoff. Because what he saw was the things he had been working very hard on doing, for 10 or more years, you could do better with microwaves with than with optical photons.
Right. It's interesting how, in a sense, like we've come back to AMO with like the neutral atom platforms that are proliferating now, right? I mean, there's now these optical tweezers with atoms in an array that can be manipulated for computation. It seems like the engineering has caught up in a sense with the superconducting regime.
Right. Well, I think the case of neutral atoms and tweezers is quite instructive for several reasons. One is that maybe 5 years ago, nobody was talking about it, and so I think that illustrates the potential for new technologies to emerge, which can really take off and lead further developments in the field. And I think we can already do pretty interesting things with those systems. There are systems of hundreds of atoms in tweezers, where you have some, which in principle you could operate as a circuit-based universal quantum computer.
And these are Rydberg arrays you're referring to.
That's right. They're Rydberg atoms. So that means they're highly excited atoms. It's pretty cool. You can a laser beam can hold on to a single atom, and then you can highly excite that atom. And when two such Rydberg atoms are in proximity to one another, they actually interact quite strongly because of their dipole moments. And you can exploit those interactions potentially to do circuit-based quantum computation, but also to do interesting analog simulations of quantum matter. Even if you don't have universal control, you can create new types of phases of matter. And we've already seen some promising illustrations of how that can lead to new discoveries. The condensed matter physicists have been hampered because they have all kinds of exotic ideas about new phases of matter, but it's really hard to make these things with electrons in material. And the AMO physicists come along and they have a different bag of tricks for realizing new quantum phases of matter with greater flexibility than we could before, where you had to synthesize a material. And
Right, and Misha Lukin's group has that result where they made the quantum spin fluid, I believe, on their neutral atom array, and Cold Quanta has a device that can produce Bose-Einstein condensates on command that you can play around with, which is pretty impressive.
Well, that Lukin experiment I think, is kind of a milestone, because the theorists have been talking about quantum spin liquids, for over 20 years. And there's been controversy about whether there are any real materials behave like quantum spin liquids.
Could have been just theory, but now we know. Yeah.
Well, yeah, I mean, so you could say, okay, well, no big surprise if you could put together atoms that interact in a certain way, and the theorists can predict that you'll get a quantum spin liquid. But things are more subtle than that for a number of reasons. You have to prepare the state, and they do it by a kind of adiabatic method where you slowly change the way the atoms interact with one another to get into the interesting quantum phase. And it didn't turn out exactly the way the simulations predicted it would. And the reason was there were different timescales that the theorists hadn't yet taken into account that you have to worry about when you're doing this adiabatic change. And so you might not wind up creating the actual ground state of the system, but some excited state. And then they had to go back, and the theorists had to figure out what had happened. So that's an example of the back and forth between theory and experiment in quantum matter, which is now possible.
You wrote the paper where you created the acronym NISQ, Noisy Intermediate Scale Quantum Machines or Quantum Devices, in 2018, and you're often sort of called on to sort of update your view on where we are, how far advanced are, how much progress are we making towards universal fault tolerant quantum devices. But I also you gave a version of that at the Solvay conference, which also included your interest in quantum matter and quantum gravity. And I just get the impression that building these devices brings the theorists and the experimentalists together for a practical, a project that has all of these added benefits that may not even be apparent when you start to try to build your first neutral atom array. That contributes back into the basic science of understanding quantum, as you said, quantum matter and quantum gravity and other topics of quantum mechanics. Is that do you see those as two distinct efforts, or do you think that's all sort of one and the same mission to try to drive the field forward?
Well, in a sense, it's one and the same mission, but I'm a physicist. I don't need to apologize for that.
No.
Engineer. I think it's really great to build quantum computers that can solve practical problems that will benefit the world, or so we hope, eventually. But I think we can be excited right now about the potential for the quantum technology for scientific discovery. And that's where I see um, things happening, on, say, a 5 or 10 year time scale.
This is great. This is exactly one of the topics we wanted to talk to you about. If you could perhaps speculate a bit, what area of experimental physics do you think would be most powerfully explored by NISQ machines now available or soon available? Do you feel like there's insight on a new area of breakthrough, which is on the verge of emerging?
Well, one always has to be a little cautious about predicting what's going to happen. But where I see a lot of potential is that one thing so of course, a big part of the question, a big part of the issue is always, can you do something with a quantum machine you can't do with a classical machine? So one thing we can say in that respect is that the methods that we know of for simulating on a conventional computer how a many qubit quantum system behaves, they start to fail when the systems become very highly entangled. You can ask about how entangled are the low energy states of a system like a complex molecule or a material, and that has a lot to do with how hard those are to simulate on a conventional computer. But there's some uncertainty about how hard those things really are classically, because we've got pretty good classical methods. We know they have limitations. They keep getting better. And for the things that you care about, if you're a chemist or a material scientist, are those systems really so highly entangled that the classical methods will fail? Not so clear. But when it comes to simulating the dynamics of highly excited matter, classical methods are not good at all, because those systems become very highly entangled and the classical methods break down very rapidly. So I think one potential area where we can expect discoveries is in very highly chaotic quantum systems, which become very strongly entangled quickly. What types of new phenomena can we find? What types of new, far from equilibrium phases of matter? Most of the study of phases of matter up until recently has focused on equilibrium phases, partly because that's what we often encounter in the lab. But with quantum computers and quantum simulators, we can start to investigate new types of matter, new phases, which are far from equilibrium.
And it's interesting. I need to go out of my way here. We have had previous guests answer the same question, and if I'm not mistaken, they've been in agreement with you. It feels like there's at least a rough consensus that this particular area is ripe for breakthrough.
Right, and I'm looking at it from the perspective of what's really hard to do with conventional computers, because that's where near-term quantum computing has the potential to show us something new.
So these odd new phases of matter. I mean, I'm just an amateur. I study this in my part time. But I mean, are you referring to things like, I don't know, spin glasses and time crystals, or is there some other domain of the world that this is pertinent to?
Yeah, things like that. Time crystals are interesting. One thing about time crystals is we call them Floquet phases. What that means is you drive them in a periodic way, and that's something you can do with a circuit-based quantum computer pretty well. Maybe more easily with a circuit-based quantum computer than with an analog simulator, which doesn't have universal control. And so I think there are such Floquet phases of matter, which are periodically driven, which we have the opportunity to discover experimentally, and then theorists can go to work understanding them. I think we also get some guidance from quantum error correction that if you consider a quantum error correcting code, but then you introduce noise, or if you change the code a little bit by changing, the Hamiltonian for which it's a ground state or something like that, the way that system um, behaves when we drive it away from equilibrium has a lot to do or is related to can we correct errors or not? And so I think we can leverage things that we've learned about quantum error correction and when it works and when it doesn't work to discover or look for new types of phases of matter. And that's also going to be interesting.
Sounds so cool. Wow, just amazing.
I wanted to make sure we made time for touching on the work that you've been doing, or that your student Robert Huang has been doing, because I think it's quite interesting. I've heard you talk about it a little bit in the past, and if I'm not mistaken, he started by sort of looking at classical shadows, and how they may relate to machine learning applications. Is that right, or is there's something? It's a fairly broad area that he's working with, and it seems.
Right. So Robert came to Caltech as a beginning graduate student in the fall of 2018, and he already had a background in machine learning, not quantum physics, but he had done research as an undergrad. He was an undergrad in Taiwan in machine learning and knew a lot about it. I knew very little about it in 2018. As an aside, I used to be a freshman advisor at Caltech. I haven't done that the last few years. But when I'd meet the freshmen for the first time, I would always ask them, what are you interested in? What are you excited about? And maybe 10 years ago, there would be all kinds of responses, a lot of them being things that I knew something about, like, oh, I'm excited about string theory or gravitational waves. Or maybe it was something like CRISPR and genetic engineering and neuroscience. But by 5 years ago, by far the most common answer was machine learning. Because they see how it's changing the way we do everything, including how we do science. And so I was lucky to have Robert as a student because I could, under his tutelage, learn something about machine learning. And he already had some big questions on his mind early in his PhD. One being, how far can we go if we, have access to quantum systems in the lab and we can measure them? How far can we go at predicting the behavior of other quantum systems, which are different from anything we've encountered in the lab before? How can we generalize from that data to make predictions for new systems? And another big question is, and how much better can we do these things if we process information with quantum machines? And so we've worked on both those questions the last 5 years.
Oh, that's interesting. I'm sorry. So it's both using classical computers and those machine learning algorithms to infer quantum behavior and quantum computing to infer quantum behavior.
Yeah, you said it better than I did.
You're kind. You went first, so no fair.
But for the first question, we've got a really big challenge, right? Because quantum systems of many qubits are very extravagant. They have, the words we use is there's a Hilbert space of unfathomably large dimension of possible quantum states. It seems far beyond our capacity as classical human beings to envision or, grasp that extravagant.
Not such an intuitive abstraction. Yeah.
But on the other hand, let's say I want to use classical ML to efficiently make predictions about quantum systems. I got to translate that extravagant quantum system. I've got to convert it into a succinct classical description, which captures physically relevant properties of the system. And that was this idea that we called classical shadows. It's a way of making measurements that are experimentally feasible today on a quantum platform, which could have, say, hundreds of qubits. And then from those measurement outcomes, we can, first of all, by classical processing, um, predict many properties of the quantum system. So, there's some properties we want to predict. What do I mean by properties? Well, physicists often talk about correlation functions. Like, I'm interested in how correlated are the uh, qubits over here with the qubits over there, and expectation values of operators that sort of act locally on the system, things like that. We'd like to be able to predict. And of course, one way to do that is just to measure that thing you want to predict over and over again until you get a good statistical estimate of that quantity, but that's very inefficient. So what we showed is by doing measurements that are experimentally feasible and are just chosen by sampling from some random ensemble, you can make predictions for a number of properties, which is actually exponential in the number of copies of the system that you measured in the lab. So that was the idea of classical shadows. And so now we have this quantum to classical converter. The classical shadow somehow doesn't tell you everything, but it tells you a lot about the quantum system. We measure that in the lab for some quantum system of interest. And now we'd like to generalize from that data to predict properties of other systems. So, I mean, a kind of a futuristic thing you might hope to do is you've got a big handbook with lots of information about different molecules where, you've measured different properties of the molecules. And now you'd like to be able, from that data, to generalize and make predictions about other molecules that you've never synthesized before.
This is the on fire topic in chemistry right now. Yeah. In ML. Yeah.
And so a lot of ML is heuristic, which is fine. So you don't have guarantees of performance. What we were interested in, under what conditions can you actually prove rigorously that you can make accurate predictions? And so we succeeded in doing that for a few different cases. And one is that you have some phase of matter, but it can be in a lot of different states. The way a physicist would describe it is there some Hamiltonian, and the ground state is the lowest energy state of this Hamiltonian. And suppose there's some family of Hamiltonians, and we sample from that family, and we measure properties of the ground states for those samples. And now we'd like to ask, can I make predictions about properties of the ground states for other Hamiltonians that are in that same family, in that same phase? We found conditions under which it's guaranteed that those predictions are accurate, and that the number of samples that you need and the amount of classical processing that you need to do to generalize is efficient.
Wow. Those are cool results. Really amazing. Yeah.
And I should put in the disclaimer that not only does Robert come up with the questions, he also answers them.
Comes up with the answers.
Well, not just Robert. We had other collaborators.
Okay. Yeah.
I can't, you had to formulate the problem and then prove theorems, and he does the numerics, and he's really been a joy.
This is really cool. So, and I mean, it's perhaps a little bit rude. Please forgive me if I'm being impolite here, because the theory, the abstraction is beautiful. But I mean, could there be a route towards applications in this domain that would perhaps, I don't know, shed new light on just ground level performance in classical or quantum ML?
Yeah. Well, I'm a physicist, so ML is great, but I want to understand things, right? I don't want ML to just be a black box that makes predictions. I mean, that's fine. I guess it's a good
No,
thing.
but that's a valid criticism of all of ML. I mean, the concern about it being a stochastic parrot. Yes.
And so we don't know quite what to say about that yet. But here's an example which harkens back to something we discussed earlier. So we have the capacity now in the lab to make new phases of matter no one's ever seen before. How do you know it's a new phase of matter? Okay. And so one of our results shows that you can efficiently learn to classify phases of matter under certain assumptions. But and so even if you, well, this is a little stronger than what we prove rigorously, but the numerics indicates that if you're sampling, states from different phases of matter, you can do unsupervised ML to sort them into different phases. Okay. In doing so, you learn some classifying function, some property of the system that tells you how phase A is different from phase B. And so I think stuff like that, as far as, again, applications to science, you might have been asking about more practical applications.
No, anything's fun. Yeah.
But as far as application to science, I think now that we have the hardware to explore new phases of matter, we're going to have to know when we found something really new instead of something boring. And so I think these tools are going to be important.
Yeah, you need a rigorous analysis tool. You can't just say it looks different, so it's a new phase. Yeah.
As to practicality, as has come up a number of times, I mean, I feel like applications in science are at least as important as applications to computer science or engineering, let's say. And in that sense, it feels to me, in a way, quantum computing is playing the role that the space race and the NASA mission was playing, as you were saying, it sort of inspired you to get into science in the first place, right? It's something that's motivating all of this collaborative co-design, experimentalists and theorists working together, physicists and computer science and engineers all working together to some outcome we're not even sure what it is, but it seems all good to us, actually.
You brought up earlier the Solvay meeting. And for a physicist, that has a certain cachet, because these Solvay conferences going back to 1913 have sometimes been places where historically important discussions take place. And so I thought it was, and this was not a meeting of engineers, really, it's a meeting of scientists, but it was experimental physicists, people who do quantum gravity, people who do quantum matter, people who do theoretical computer science, who have enough in common that we can have fruitful discussions and share ideas. And the fact that there was a Solvay conference, which mostly in the past has been either about high energy physics or condensed matter physics or astrophysics, where the theme of the meeting was the physics of quantum information, is an indicator of where physical science is heading. And I think a lot of the excitement comes from these connections between fields. That really stimulates progress.
It's fantastic. That seems like a terrific time to a place to end up. That's really a great sort of feeling for the enticement of the field and the promise of the field. And thank you so much for being with us, John. It's been
Thank you
pleasure.
so much, John. Really, yeah.
Are you telling me an hour is up already?
That's right, exactly. You have a meeting to get to.
I was trying to be respectful of your time, but also, yeah, it did fly by. Yes,
we were having so much fun.
Yeah,
we really enjoyed this. Thank you so much.
Yeah, thank you.
All right, thank you.
That was a great conversation. Super
cool.
Interesting. It's such a privilege to be able to talk with people who've been around from pretty much close to day one. I mean, as John said, he overlapped at Caltech with Feynman for about 5 years.
Yep.
And he's been tracking and involved in the field since Deutsch's paper in 1985. So his roots go very, very deep, and he's he has such an interesting take on what the threads are that are critical to his sort of understanding of how the field's progressing.
So cool. I think also I was really thrilled by the work of his graduate student on his team, Robert Huang, in terms of the cool applications of machine learning and quantum information science. There's just that's a rich theme that just keeps coming up in these interviews. So wow, I think much more along these lines to come. But I can't wait to see more of this guy's work.
Absolutely, and it is exciting because when I first encountered quantum and machine learning in the same sentence, it was using quantum computers to somehow accelerate machine learning, which they've got a long way to go in that regard.
Yes,
but using ML and using the enormous classical computing power that we have with those algorithms to better understand quantum systems, to exert classical control in these quantum systems, that's extremely promising from a scientific perspective, but also from an engineering, manipulation and control of these systems. Maybe we get better error correction through ML and other techniques as well. So very interesting.
We live in very interesting times.
As we say, most episodes, it's the best part of this podcast is how mind-blowing these conversations are.
So cool.
Yeah. So thanks for joining us. We hope you enjoyed it. If you did, please subscribe and leave a review on Apple Podcasts or Google or whatever other platform you listen to. And we'll catch you again next time.
Looking forward to next time. Okay, that's it for this episode of The New Quantum Era, a podcast by Sebastian Hassinger and Kevin Roney. Our cool theme music was composed and played by Omar Costa Hamido. Production work is done by our wonderful team over at Podfi. If you are at all like us and enjoy this rich, deep, and interesting topic, please subscribe to our podcast on whichever platform you may stream from. And even consider, if you like what you've heard today, reviewing us on iTunes and or mentioning us on your preferred social media platforms. We're just trying to get the word out on this fascinating topic and would really appreciate your help spreading the word and building community. Thank you so much for your time.